Hello guys, welcome to today's lessons. So for today we are going to be considering linear first order differential equations. So in learning linear first order differential equations, you need to know the general form of expressing linear first order differential equations like this. It's actually dy by dx plus p of x y is equal to q of x. So this is the general form of expressing linear first order differential equations. So the next question is, how on earth do we solve linear first order differential equations? Well, we can't apply method of separable variables here because it's not just going to work. So we need to devise another means, and the answer to solving linear first order differential equations is through the use of integration factors. Okay, so we solve these equations, right, using integration factor. Now let's see what this integration factor is or looks like. So supposing we want to solve these differential equations, okay, first of all you need to know that every linear first order differential equation, to call it linear, you have to express it in this form. Okay, this must be the way that you must express it in this form: your dy dx, then your p of xy, then your q of x. P of x and q of x are called coefficient functions. Now take note, they could be constant sometimes, or they could be functions of x. So whichever variable that you, or whichever is the case, you still have to try as much as possible in order to use the linear first order differential equation approach. You must express it in this form so that you can be able to solve it. So how do we solve it, and what are the underlying assumptions that we make to solve this particular problem? First of all, we are going to assume a function mu of x such that whenever we multiply this function by p of x, we are going to get mu prime of x. This mu prime of x is still d by dx of mu of x. Is that okay? So this is the first assumption. Now this mu of x is called the integration factor. Mu of x is the integration factor. Integration factor. Now, since we have assumed that anytime we multiply mu prime of x, since we have assumed that our mu prime of x is actually the multiple of mu of x times p of x, see what happens. You discover that this mu prime of x is still the mu by dx for short, and is equal to mu n times p, both functions of x. Is that okay? Now we can separate the variables here. So 1 over mu, the mu, is equal to p dx. So this when we integrate, you will have 1 over mu is equal to integral of p dx, and this gives me natural logarithm of mu is equal to integral of p of x, or p of x with respect to x. Now if we take the exponential of both sides, we will have mu is equal to exponential integral of p dx. So this is going to be the value of the integration factor. Okay, this is going to be the value of the integration factor because of the assumption that the integration factor is such that whenever you multiply mu of x times p of x, the answer should be the first derivative of mu of x. So after we now solve, we now discover that our mu of x is now going to be a function of a function. Mu of x is an exponential function that its argument is actually the integral of p. And where is this p coming from? P is coming from our linear differential equation over here. Okay, so the next question is, how on earth do we apply this integration factor? So this is how we apply the integration factor. Now, since we have already gotten to know what it is, we are now going to multiply the linear form, the linear differential equation by mu of x. Now when we multiply it, we get mu of x dy dx plus mu of x p of xy is equal to mu of x times q of x. Okay, so what I just did was, this was the differential equation over here. That's the general form of a linear differential equation. So we just multiplied every term by the integration factor, which is a mu of x. Now remember our assumption that anytime you multiply mu of x and p of x, what are you supposed to get? That's right, you're supposed to get mu prime of x. So if you write this particular differential system of equations, you have differential equation, sorry, not system, you have mu of x. So mu of x times p of x is actually going to be d mu of x dx. Then you now have your y is equal to mu of x times q of x. Now if you can agree with me, there is something interesting happening on the left hand side over here. Now let's establish something. Assuming we want to differentiate with respect to x a u dot v product rule, what do we get? We'll have u, then we'll differentiate v, and all we'll have v, then we'll differentiate what? U. Is that not how we normally do it? Okay, so this product rule. So this is exactly the same thing that is happening here. We have mu of x, we differentiated y, then we now have the derivative of mu of x and we held y. So in other words, this left hand side can be reduced to d by dx of the product of mu of x and y. Okay, why the right hand side still stands as this. So at the end of the day, you can now see d of mu of x times y is equal to mu of x times q of x dx. So if you integrate both sides, d mu of x y, you have the integral of mu of x q of x dx, like this. So they are now trying to tell us, remember, when you integrate the something, the simplest formula on integration, when you integrate the something, you get something plus c, but I'm not going to put the integration constant on this side. So we are integrating d something, and in this case is going to be that something, which in this case is mu of x times y. So this is the resolution of the left hand side, which resolves to u of x times y. Then when you now integrate this particular guy, which we don't yet know, we can just leave it like this. So at this point, this is how we have arrived at the formula that we are going to be using to solve first order linear differential equations. And remember that our mu is actually exponential integral of p dx. Okay, so after you get your mu, there are two things involved. If you want to multiply through by the integration constant with integration factor, which is mu, you will multiply through. Definitely the left hand side will now reduce to the product of the integration constant times y, and the right hand side will be the integral of your mu of x times q of x dx. Remember, this is the general form. The general form is y prime plus p y is equal to q. So every linear differential equation must conform to this standard. Take note, this is a plus sign. So if there is no plus sign, you have to make the plus sign to be there somehow, and we're going to solve some examples to see how it is. So to find y, remember, obtain your integration constant, then you can use this formula. So depending on the scenario you may be working with, you can use this formula directly. It's allowed. In fact, according to findings from K.Strout, what I learned back in the days was y multiplied by if, which is integration factor, is equal to integral of q multiplied by if dx, like that. Okay, so this is just still the same formula. So after you integrate this right hand side, you're now free to divide both sides by the integration factor so that you can obtain y alone. Okay, so that will give us our general solution. So we are going to solve some more examples to see this, but so far you have just learned the background of linear first order differential equation, how it came about, and the general assumptions that we used to tackle the problem. I think people who created the techniques are really very intelligent. For them to come up with something that will reduce this left hand side to the products of an integration factor, a term called the integration factor, and y. Okay, so everything is just taking us back to this critical assumption that was made here, over here, that our integration factor should be that whenever we multiply it by p of x, it must evaluate to this term mu prime of x, which is still in the mu here. So I hope you understood this video. If there's any place that is not clear, please leave comments and I'll be glad to attend your question. In the meanwhile, next video I'm going to be looking at examples in solving linear first order differential equations, and we'll see how to apply these formulas and see short ways of resolving our problem, and still continuing in our journey of learning how to integrate more perfectly. So thank you for watching, and I hope to see you in the next video. Like, subscribe, share to your friends, hit the notification button to stay updated on latest videos I'll be released. So thank you very much, and till next time.